Welcome to the third episode of the History of Science seminar this year at IAS. The last one will be next week. It'll be Stephanie Dick, historian of mathematics, who will be coming and giving us a talk. But we're honored and pleased to have today's guest. We're welcoming him back to the IAS because the talk that he will be given today, he started as a member back in 2012, 2013 in the School of Historical Studies. Chen-Pang Yeang is an associate professor at the Institute for the History and Philosophy of Science and Technology at the University of Tirana. He received a Doctor of Science degree in electrical engineering from MIT, as well as a PhD in STS from MIT. He studies the histories of physics, digital technologies and cultures, electrical engineering, and computer and information sciences in North America, Western Europe, and East Asia from the late 19th century to the present. Please turn off your cell phones. He's published numerous articles as well as two books. The first one, Probing the Sky with Radio Waves from Wireless Technology to the Development of Atmospheric Science. That was published 11 years ago, 2013, with the University of Chicago Press. And this book, which he'll be speaking today. Again, that's the project he started here in 2012, Transforming Noise, a history of the science and technology from disturbing sounds to informational errors from 1900 to 1955 with Oxford University Press. It came out in the fall, right? If I'm correct, was it fall or summer? 2023? Oh, in January. I got an advance copy. So it's 2024.
To be 2023, but
okay. Okay, we're always slow here. That makes sense. He's working on three projects currently, three book projects. One is they include grassroots innovations of digital technologies, China, Taiwan, the US. Heinrich Hertz's electric waves and the replication of scientific effects. Is that with Jed? Yeah, with Jed Buchwald, Chao Yun Ren, and the soundscape of Republican China. He's also examining the history of quantum computing and communication. And I'm really fired up about this book since it's very similar to the book that I just finished, but telling the German rather than the American story. So please join me in welcoming back Chen Yen-Pang. Welcome back,
Chen. Thanks a lot for Miles to inviting me back. Good evening, everyone. Welcome to this colloquium talk. As Miles mentioned, this is a sort of homecoming journey for me because 11 years ago, I was a member at the School of Historical Study, and I started this project at the School of Historical Study, and I remember I gave a colloquium talk there at that time. And now it's sort of the end of that journey for this project. So I'm really honored and appreciate it. As Miles mentioned, this is a book published by Oxford University Press in 2023, came out in North America in early 2024. And this is, the book title is Transforming Noise. So today I would like to give you a sort of free sneak previews of the sort of some major contents of the book. But I want to start with two quotes of two texts which separates about 100 years or more than 100 years apart. So the first quote came from the American author, fiction writer, Nathaniel Hawthorne. So the year was 1844. Place was Concord, Massachusetts. So in July of the year, Hawthorne sat at the meadow, a long, quiet, pasture-like place near a forest, and he was sitting there enjoying the July sun. Of course, a little bit warm in New England at the time, but still, he was looking for literary aspirations. So he reported something, and he wrote it in his diary. So in this quote, well, here, let me just read it. So he said, but hark, there's this whistles of locomotive, the long shriek harsh above all other harshness, for the space of a mile cannot mollify it into harmony. It tells a story of busy men, citizens from the hot street, who have come to spend a day in a country village, man of business, in short, of all uniqueness, and no wonder it gives such a startling shriek, since it brings a noisy world into the midst of a slumberous peace. So he was sitting in this lawn and hearing the sounds of trees, like leaves falling, and enjoying the bird chips, and some farmers just mowing the grass. And then a sharp shriek of locomotive sound just came by, and he was impressed by this sort of intrusive sound. So he reported this. Well, of course, there's a story to say about that. The literary critique, Leo Mars, gave the term machine in the garden to describe this kind of moment in American literature. But what I want to stress here is that he noticed some loud sounds and he reported this as noise. So for people at Hawthorne's time in the mid-19th century, at the height of Industrial Revolution America, noise was sounds, right? Noise was purely sonic attributes. And then more than 100 years apart, the year is now 1986, and the author is Fisher Black, and he was the, well, at this time, he was the chief analyst of the financial analyst firm, financial firm Goldman, investment firm Goldman Sachs, and he published paper with the title Noise in the Journal of Finance. So in this paper, noise has nothing to do with sounds, right? Here, just looking at the abstract, you can tell what kind of noise he's talking about. So here's it. He says the effect of noise on the world and on our views of the world are profound. Noise, in the sense of a large number of small events, is often a causal factor much more powerful than a small number of large events can be. So here it's not talking about disrupting sounds, but talking about a huge number of small yet random fluctuations, random events, right? So indeed, today, we encounter the Fisher's sense of noise everywhere. So we encounter noise when we talk about, for example, the transmission rate of COVID-19 or the genetic pathways of E. coli, or the stock prices, or the vibrations of the the gravitational waves from remote galaxies, or the data from political poll from the elections, or the global climate change data. So noise is everywhere in this in our sort of data-rich, information-rich society, and noise in these senses had very rarely to do with sounds. But if we go back to the 19th century or even earlier, then noise was primarily about sounds, right? So when you go back to, for example, early modern periods, you ask any random person on the street and you ask him or her what noise is, then it turns out that noise is nothing but this sort of all kinds of sounds in the vibrance, in a sort of chaotic, disorderly, sonic environment or soundscape on the street, right? Like Peter Bruegel's painting, Carnival Battles Lanes. So from disturbing sounds to informational error, there was indeed a profound transformation that happened, right? So, but how do we make sense of this transformation? Well, on the one hand, of course, we can say that this transformation is semantic. It's just a change of words meaning, right? But here, I think it's useful to evoke a thought of another literary scholar named Raymond Williams. So in the 1970s, Williams wrote this book called The Keywords. So in this book, he highlights like between 50 and 100 what he deems as keywords. And he believed that these are keywords because they can be, these are the words that undergo dramatic, substantial transformations within a shorter period of time. And he believed that the semantic transformations of these words actually can serve as a barometer of the social or historical processes at large, right? So it's in this sense that he called these words keywords. So similarly, I believe that we can also understand noise from this angle as a keyword. But it's only that the noise as a keyword does not really happens in the kind of political, societal, cultural realms as Raymond's characterized, but rather in the realms of science and technology. So specifically, I think if we look at the semantic and more than semantic transformations of noise, we can see three, we can use it as a barometer or as a lens to see three sort of fundamental processes and undertakings in 20th century science and technology, right? So one has to do with sounds. So how scientists, engineers, technologists understood sounds. How did they cope with the reproductions of sounds? And how did this happen in an increasingly capitalistic and increasingly confrontational worlds in which we see corporate research and mass media, etc. And the second realm has to do with chance, right? So how to understand random fluctuations, how to understand the probabilistic events. So these are long-standing questions, probably dating back to the early modern periods. But in the 20th century, with the studies of noise, these questions about chance, probability, statistics, again, new meanings. And then the third realm has to do with information. So how to sort of understands and cope with information, cope with data, cope with computing, communication. So again, this, even though we can trace this back to earlier period of time, in the 20th century, especially by the mid-20th century, we can see some new developments associated with particularly World War II, but also industrializations of communication technologies. And so this is what I'm going to, so these three realms of issues are what I'm going to address for the rest of the talk. And to address these issues, I sort of divided the historical developments roughly into four pieces or four chunks. So in the first period of time around from 1900s to 1920s and 30s, we can see the increasing abstraction and materializations of noise into something just away from sounds to something more abstract and symbolically manipulable and measurable. And then around the same time, we see the developments of the Brownian motion theories and the theory of random fluctuations, and eventually leading to the studies of electronic noise in the theoretical sense and also experimental sense. And then between the two world wars, we see the three theoretical approaches that further develop the theories of Brownian motions and the theories of random fluctuations by physicists, mathematicians, and engineers. And then finally, during World War II and after the war, we see how this coping with information, communication, computing gave rise to a new regimes of dealing with noise that has to do with the sense of random fluctuation, which we will see. Okay, so the first part first. So if we go back again before the 20th century, then noise, as I said, was primarily sonic. And before the 20th century, there are roughly two major meanings of noise. So one has to do with this idea that noise is a discordance or disharmony or disordered sounds. And this kind of thought was particularly prominent in musical history or in the physiological or physical studies of music and sounds, right? So a representative figure along this line of thought was Hermann Helmholtz, 19th century physicist, German physicist, physiologist. So in Helmholtz's characterization, noise is basically accomplished, as he said, accomplished by a rapid alterations of different kinds of sensations of sound. So the basic idea is that noise is combinations of many different sounds with simple harmonies, but when they combine together in an irregular way, that's noise. But in addition to this idea of noise as disharmony and discordance, there was another powerful meaning of noise, and that refers to noise as nuisance, especially from the industrial and urban life, right? So in this sense, noise had more to do with the sounds from without, sound that was intruding into our environment, into our lives, and we have to control it, we have to cope with it, we have to protect it from happening into our environment. So this, of course, was especially prominent during the Industrial Revolution when this so-called noise abatement began to be more and more frequent in many countries around the world, right? So, but when by the end of the 19th century, this meanings of noise began to change gradually and piece by piece from this purely sonic sense of sounds into something more than sounds, right? And a large of it had to do with the sound technologies, or in particular, the technologies that reproduce sounds through electrical or mechanical means. So that includes, for example, Thomas Edison's and Emil Berliner's inventions of phonograph, independently, of course, or Alexander Graham Bell's inventions of the telephone, and also the wireless or radio introduced by Marconi's and others, right? So in this sounds reproduction technology, as the technology developed and spread into people's daily life, this technology began to turn noise into material factors and measurable quantities. So one thing in the early sound reproduction technology was this discourse on what they call the surface noise. So these notions of surface noise began to appear in the early 20th century when phonograph, the sound recording machine, was turned from an office machine or a toy into something like a music reproduction machine, right? Into a machine that people use to enjoy the music. So by that time, the enthusiasts of a phonograph began to appreciate or pay more attention to the fidelity of sounds produced by the phonograph, and they began to notice some unpleasant sounds coming from the machine, and they give the name surface noise to those kinds of sounds. So according to that characterization, this surface noise had to do with the defects of mechanical inscriptions on the recording media, like the cylinders or disc phonographs, and then this mechanical defects on the surface of recording media was translated into a sonic effect, into noise, right? So, so the implications of this concept, surface noise, was not only about the disturbing sounds as the noise had been used to characterize, but also the noise was used to characterize unwanted effect on fidelity, in this case, the mechanical defect. And then by the early 20th century, another developments come to forth. And then in this developments, as I mentioned, noise abatement became a severe issue, and cities around the world, especially in North America and Western Europe, began to take all kinds of policy measures and social movement measures to cope with noise in our environment. So one measure that was taken was to try to measure the quantity and the sonic characteristic of noise, to measure the din, right? So in this context of noise abatement movement to cope with environmental sounds, a new instrument was introduced specifically for the purpose of measuring noise, and that was AT&T's number 1A audiometers in the early 1920s. So this 1A audiometer was adapted from the machine that was originally designed to measure the to measure the hearing, the audibilities of those with hearing despair, But then it was converted from these instruments for measuring the hearing capacities of people's hearing into into a measuring device for environmental noise. And the principle underlying this instrument was the so-called ear balancing method. So in this method, there was a measurer or operator, and this person take turns in hearing the external environmental sounds and adjusting the reference sounds, which appears on another ear, on the other ear, and this person just compare the two sounds and adjust the reference sounds until the reference sound reach about the same level as the environmental sound, and this person takes that reference sounds level as the level of environmental sound. So this is called the ear balancing method. So this method was initially used to measure the urban environmental noise, but soon, by the mid-1920s, it was used to measure another kind of physical effect, which at this time was also began to be called noise, and that was atmospheric noise. And this was especially relevance in radio communications. So by the early 20th century, radio and wireless engineers discovered that the irregular atmospheric discharge created fluctuating electricity, and this could affect the quality of communication. And this was called the atmospheric noise, right? So, and there's little means to control this kind of atmospheric noise because it came from the atmosphere. So to the engineers at this time, the best way to cope with this noise was to measure it, right? So in 1923, AT&T developed its first transatlantic high-frequency wireless communications, voice communication system. And to test the system, AT&T devised an year-long experiment to do the transatlantic test, and including a sort of regime to systematically measure the atmospheric noise for the transatlantic wireless communication. So in this measurement, the AT&T engineer utilized the ear balancing method to measure the atmospheric noise. So by this, they actually converted this atmospheric discharge as a physical effect into some semantically equivalent concepts of sonic noise, and began to use noise to refer to this atmospheric discharge, right? So remember that the ear balancing method depended on the perceptions of the measurer, of the operator, right? Because it relied on the operator to judge that this sounds, the reference sounds, was at the same level of the sound to be measured. But and this applies also to AT&T's measuring schemes for transatlantic wireless communications in the early 1920s. But around the same time, another group of researchers had different ideas about measuring the atmospheric noise. So a leading person in that campaign was Robert Watson-Watt, a British physicist. So he began to use not the ear balancing instrument, but the oscilloscope to display the waveform of atmospheric noise. And he believed that by doing so, he could wave out the interventions of human subjectivity and make this measurement purely objective, right? So that doesn't mean, however, that this so-called objective measure of the waveforms of atmospherics took over and became dominant over other means. So by the 1930s, we can see a plethora, a variety of different ways to measure atmospheric noise, or to measure the environmental noise, sonic noise whatsoever. So these regimes of noise measurement included, for example, the ways to measure the overall power of noise, or the spectrums of noise, or its waveforms like the oscilloscope, or its loudness like the audiometer. So here we can see interesting tension between measuring between the emphasizing mechanical objectivity and the authenticity to sensory experiences. Okay, so while these engineers and technologists were developing ways to measure noise, there was another group of people who were more interested in the theoretical understanding and modeling of noise. And the theoretical resource that they utilized had a lot to do with this long-standing discovery or phenomenon called the Brownian motion. So the Brownian motion was discovered as early as the 1820s by the Scottish botanist Robert Brown. So basically, it refers to these rapid and irregular motions of small particles in but visible particles in the liquids. Right. So for a long time, physicists, biologists in the 19th century have been debating about the reasons of the Brownian motion. But then at the turn of the 20th century, there was a new threads of theoretical breakthrough for the studies of the Brownian motion. And this breakthrough has to do with the transitions of statistical mechanics around that period of time. So when statistical mechanics was developed in the 1870s or so, it was originally used to sort of explain the thermodynamics in equilibrium, right? So it was basically a statistical average to try to recount for the phenomena like the ideal gas law. But then by the early 20th century, more and more physicists looking into statistical mechanics began to look beyond this studies of thermal equilibriums and look at the fluctuation phenomenon. So critical opalescence or density fluctuations are those kind of random fluctuations that came to their attention. And then Brownian motion exemplify exactly this kind of random fluctuations, right? So one of the most famous people to give the breakthrough of this theoretical developments was Albert Einstein. So in 1905, of course, this was a big year for Einstein. He introduced the theory of relativity and the hypothesis of light quanta. But in addition to that, he introduced a theory of Brownian motion. So in this theory, Einstein argued that the Brownian motion, the random motions of irregular motions of these small particles are due to their collisions with molecules, with water molecules, right? And the trajectory of each of these particles is a random time variant process. And these particles' trajectories, these random processes, are independent between different particles. And even from time to time, like in the small segments of the trajectory, it is independent statistically from another small segment, right? And he used the probability density distribution function to characterize the number of particles with the displacement between these small windows, spatial windows, from time 0 to t, and from various calculations considering the continuity condition, he came up with the governing equation for the probability distributions of Brownian particles, which is in the forms of the diffusion equation. And there's a simple solution for the diffusion equation, which takes the forms of the Gaussian distribution, only that the width of this Gaussian distribution is spread over time, right? So that's why the Brownian motion spread its volume ever larger and larger and larger. So Einstein was not the only person to make this kind of breakthrough. So around his time, there are two scientists independently working on Brownian motion. And one was Marian Smoluchowski. So he was a professor at University of Lvov, today's Lviv in Ukraine, but at that time, a city in Austria-Hungary. And Smoluchowski was a Polish. So he introduced a similar theoretical framework of Brownian motion as Einstein's Brownian motion, as Einstein's theory, but Smoluchowski had closer contact with the experimental community, so he emphasized more the random walk properties of the Brownian motion and under the experimental situations of ultra-microscopic observations. Another person who made contribution to this theoretical study was the French physicist Paul Langevin. At this time, he was professor at the ESPCI in Paris, and he, in 1907, introduced a stochastic differential equation to characterize the Brownian motion, which is different from the probabilistic characterization. So in this, he write down the equations of motion with the stochastic force representing the random collisions of molecules onto the particles. So in these works by Einstein, Smoluchowski, and Langevin, of course, the long-standing traditional wisdom is that Einstein's discovery testified to the realities of molecule, and that's true. But on the other hand, Einstein theory not only provides strong evidence for the reality of molecule, but also provides some characterizations of a new mathematical entity, which is a random process, right? And moreover, this fluctuation studies imply that the microscopic randomness, these molecular collisions, can lead to macroscopic fluctuations, right? And that can happen in the case of Brownian motion. That can also happen on some other realms. For example, in the late 1900s, Einstein and H.A. Lorenz's daughter, Gertruda de Haas-Lorentz, so they independently argue that there might be a possibility that if we have an electric circuit with no external power, but due to the random fluctuation, the Brownian motion-like movements of the electrons, free electrons, we can detect this fluctuating electric currents, right? So by connecting the capacitor to a galvanometer, we can, in principle, detect this weak fluctuating current. But Einstein quickly denied the possibility of ever measuring that because he said that intensity was too weak to be measured. However, this situation began to change by the 1910s, right? So a large factor for the change had to do with the inventions of vacuum tubes. The thermionic tubes was introduced in the early 20th century, first as a detector of radio signal, but then by the early 1910s, it began to be used as this weak signal amplifiers, right? And this weak signal amplifiers became especially important at the time of World War I, when the militaries in the war-engaging countries began to invest resources for wireless communication systems using vacuum tube amplifiers. So it was under this context that a German physicist, Walter Schottky, proposed a theory in 1917. So in 1917, this was at the thick of World War I, and Schottky at this time was the head of a research laboratory at Siemens Hauske Gesellschaft in Berlin. And the laboratory was dedicated for the research and developments of radio communication systems. So Schottky, therefore, was familiar with the vacuum tube amplifiers. So in this paper, he argued that if we consider an electric current flowing through a vacuum tube, then it is by no means a flat current, a steady flows of electrons, right? Instead, because this is constitutes the trains of electrons. So each electron is a discrete charge. So the actual current should be more like this. Instead of constant flow, we are expect to see a trains of pulses in reality. And the difference between the constant flow and the trains of pulses give rise to our perceptions about fluctuating currents and our sonic perceptions of noise. So he gave the name Schott effect, or later on in English called the Schott noise, to this kind of random fluctuation. And he also developed theories of the Schott noise based on some techniques that his PhD supervisor, Max Planck, had utilized in the early 20th century for dealing with black body radiation. And in the 1920s, in 1910s and 20s, on the other side of Atlantic, there was another group of engineering research scientists who were touching upon these issues of electronic noise. And these people came from AT&T. So after World War I, AT&T planned to expand its telecommunication empire and build up this transcontinental telephone network. And of course, when you want to transfer messages from the East Coast to the West Coast, you have to repeat and relay the signals. And those signals needed strong, powerful electronic vacuum tube amplifiers. So that gave the AT&T researchers a reason to look into the performance of electronic amplifiers. So in the mid-1925, John B. Johnson at AT&T Bell Labs conducted experimental trials on a large number of on-the-shelf vacuum tube amplifiers. And he found that in this kind of vacuum tube circuits, the noise measured from these amplifiers actually had a lower bounds, which is proportional to the gain or amplifications of the circuit. So because of this lower bound, Johnson suspected that this noise at the lower bound has nothing to do with the vacuum tube, but more to do with the input resistor. So he suspected that there was intrinsic noise that is related to the electrical resistors. So later on, Harry Nyquist, another AT&T researcher, developed a theory to explain this kind of resistor noise, and he gave the name thermal noise because he argued that the reason why there is such a noise is exactly because a resistor has many electrons, free electrons flowing in, and under the non-zero temperature, those electrons are undertaking Brownian-like motions. And this electronic noise or thermal noise is exactly the results of the thermal motions of free electrons, right? So for both the shock noise and the thermal noise, the random fluctuations due to microscopic randomness actually give rise to visible effects like the Brownian motion, right? And moreover, from the theoretical conclusions, both noises are called the white noise in the sense that their energy or their power is the same across different frequencies, right? And therefore, and since both noise is there, the engineers, in order to control this noise, they wanted to do more theoretical studies and more measurements on this kind of electronic noise. So this leads to the further developments of the theories of noise during the interwar periods. So briefly, during this period, there are three different groups of people who try to develop further the theories of random fluctuations. So one were statistical physicists, one were electrical engineers, and the third group were pure theoretical mathematicians. So a representative figures of the statistical physicists working on the theories of random fluctuations and noise was George Uhlenbeck. So he was trained at University of Leiden in the Netherlands, but then got a teaching position at the University of Michigan in the late 1920s. So for Uhlenbeck, the noise appears, or random fluctuations appears in different kinds of problem situations, including like the wobbling of galvanometer mirrors or the fluctuations of particles under ultra microscope, like the Brownian motion. So for him, it was important to recognize the commonalities of these different kinds of fluctuations. And what he and his fellow traveler statistical physicists did was to try to formulate the dynamics or the time evolutions of the statistical properties of those random fluctuations. So the idea is that Einstein and Smoluchowski or Langevin, they consider the equations for stochastic equation dynamics of force or the equations of probability distribution, but they didn't include other complicated factors like the external force. So people like Uhlenbeck moved further to make refined derivations of the equations under different circumstances, and they came up with the time evolutions of these statistical properties. So in that regard, they're following the sort of long-standing tradition in statistical physics is dating back to the days of Boltzmann that follow the convergence of a dynamic system toward equivalent, and therefore pay close attention to the time evolution. So the second group of people were electrical engineers. So they were more interested in filtering out noise in telecommunication system. And especially one event or one invention especially triggered their further interest in the theoretical studies of noise. And that was Edwin Armstrong's introductions of FM radio in the early 1930s. So FM radio, you may know that the FM radio system actually was much more noise susceptible, so it had much higher signal to noise ratio. Therefore, these electrical engineer researchers were wondering about why that was the case. So John Carson, as a researcher at AT&T Bell Labs, was especially intrigued by this kind of the performance of FM, and therefore went further to develop a theoretical modeling of noise in the telecommunication system. So for these electrical engineers, noise had a simple model. So basically, they're not interested in the time evolutions of the dynamic system. Rather, they assume noise as either a single harmonic components in conjunction to the signal, or as some random fluctuation with wide spectrum with equal energy at different frequencies. And using that, they calculated the signal to noise ratio at the input and the outputs of the telecommunication filtering and modulation system, right? And their purpose was to look at the values of signal to noise ratio. So this is two totally engineering consideration. But then there was a third group of people, and these were mathematicians, and they were part of this larger mathematical movements at the turn of the 20th century. So some of this movement came from the needs to find the foundations of probability theory, like what Kolmogorov did in the 1920s or so, or the measure theory of probability in the theory of analysis in mathematics, or ergodic theory. But the representative figure, again, along this line of movement was the American physicist Norbert Wiener at MIT. So in the early 1920s, Wiener published a paper that tried to formulate the Brownian motion as a kind of random process in what he called the differential space. So then basically this is the idea. So if we consider a stochastic process f of t, then for Brownian motion, the difference between its value at two different time instants it represents the Gaussian distribution with zero means and variance proportional to t minus s, right? And this guy is independent of the difference in another time sector, and therefore we can actually expand this random process in terms of the values at different time segments, x1, x2, etc., to xn. And this x1, x2 to xn, they can be used as a point in the hyperdimensional space. So we can use this space to represent each random process as a point. And this space is what Wiener called the differential space. So another mathematical breakthrough that Wiener explored had to do with the frequency analysis of random fluctuations. So as early as the 1920s, engineering scientists knew that both shot noise and thermal noise were white, right? However, if you try to use the traditional Fourier analysis, then it doesn't work, because in the traditional Fourier analysis, the Y spectrum corresponds to an impulse, right? Not a random fluctuation. So what's going on here? Well, so in order to solve this problem, in the 1930s, Wiener, I'm sorry about the sort of scrambling of the symbols. But anyway, so Wiener, and independence of him, Alexander Kingshan, in Moscow independently came up with what is later called the Wiener-Khinchin theorem. So basically, the theorem says that if we want to analyze the spectrums of a random fluctuation, we should take its correlation function and do the Fourier transform instead of trying to do the Fourier transform on the waveform itself, right? So that's the Wiener-Khinchin theorem. And this actually had a profound effect on the subsequent processings of random fluctuations in the 1940s and onwards. So that leads to the discussions of the last part, which has to do with the further theoretical developments of noise during World War II and afterwards. So in this period of time, especially during World War II, the researchers coming from different traditions, including physicists, mathematicians, and engineers, they came to cope with the war-related defense projects and try to utilize the theories that they had developed in the 1920s and 30s to the war-related military defense projects, right? So in doing so, they actually began to entertain a kind of ontology or worldviews, which I call the ontology of the ambience. So in this ontology of the ambience, they're actually conceiving a trilateral relationship between human, machine, and environment, right? So in this, and this can apply to not only telecommunication systems like radio, but also things like radar or anti-aircraft gunfire directors or encrypted communication systems, right? So in their modeling of the environments, in this ontology of the ambience, environment is indeterministic, chaotic, stochastic, and haphazard, right? So, and this kind of chaotic disturbance and fluctuations was modeled exactly in terms of noise. And this noise that they were considering at this time was primarily additive, and it had Gaussian distribution, and it was primarily continuous, right? And all these assumptions didn't have to be valid for any kind of circumstances, but for various reasons, they just subscribed to this kind of model. So one group of people who were pursuing this line of research during the war was led by Uhlenbeck, right? So during the war, Uhlenbeck headed a theory group at MIT Radiation Labs, and he had two assistants or two collaborators helping him. One was the Cornell mathematician Mark Hash, who was Polish immigrant and actually refugee to that extent because he was a Jew. And another person was Wang Mingzhen, and she was Uhlenbeck's PhD student, but she graduated from the University of Michigan, but landed a job at MIT Radiation Lab during World War II. And their job was to deal with the noise in the radar detection problem. So basically, in the radar system, you project the signals along with noise on the screen. So the screen was much cluttering and noisy. And you want to figure out whether, for example, this bright spot is actually due to some target reflection or due to some cluttering or noise or environmental disturbance or whatever kind of noise, right? So that was called the threshold signal problem. So basically, in order to deal with this threshold signal problem, Uhlenbeck, Kash, and Wang, they argue that there is this close analogy between the radar detection problem and the galvanometer problem that they deal with before World War II in statistical physics, right? So in that regard, the radar noise actually was similar to the Brownian motion. So what they're looking for is the constructions of this thing called the batting curve, which represent this the success of signal target detection in terms of the signal strength. So in other words, they're asking how strong a signal should be in order for the target detection to be successful within like 80% or 90% or so. So what's the threshold level for the target detection to be successful? So that's the threshold problem. To solve that problem, they utilize the statistical method that was developed before World War II in the dealing with random fluctuations. So another problem that came to this researchers' attentions about noise was the anti-aircraft gunfire directors, right? So, and of course, this was a problem that was dealt with by Norbert Wiener. So there's a rich historical literature about Norbert Wiener's dealing with the anti-aircraft gunfire director problem, leading to his theories of cybernetics. So basically, Wiener considered this problem of anti-aircraft gunfire directing as a prediction problem. So he treated the enemy targets as a signal and all kinds of observational errors as noise. So the inputs to the director is signal plus noise. And the objective is to predict the futures of the signal for a few seconds, because you have to aim your gunfire a few seconds ahead your enemy's movement in order to shut the enemy targets, right? But you have to filter out that noise, that errors, right? So it's a stochastic signal and noise problem, and you have to develop a scheme to filter out the stochastic noise and to do the predictions of the stochastic signal. So he came up with the theories, which was utilizing heavily his pre-war theoretical developments on the generalized harmonic analysis, and then he assumed the noise to be white Gaussian, and the solution was a kind of filtering, right? So this was another realizations of the sort of pre-war fluctuation theory applied to the war-related defense project. And the third war-related defense project on noise was introduced and put forward by Claude Shannon, right? So during the war, this American mathematician working at AT&T Bell Labs worked on several projects, including theoretical analysis for American Army's secret encrypted communication systems. So in that theoretical work, Shannon actually came to the thought that, okay, so if we are considering the encryptions of a secret communication system like the German Enigma, right? So every morning, the German High Command issued a random key to encode the system so that we don't know what the random key is. So it's very likely that for the same message, you get different ciphers because of different random keys at different days. So this random key actually creates equivocation in the sense that the two different transmitting signals can lead to the same receiving signals, or vice versa. The same transmitting signal can lead to different receiving signals, right? So to Shannon, this equivocations in the encrypted communication due to random key is highly similar to noise, in the natural noise. So this actually gave him some inspirations for his post-war constructions of information theory, which he published in 1948, and the mathematical theory of communication, right? So in that theory, he dealt with the part called the channel coding theorem, in which the communication happens from a transmitter going through a channel corrupted by an additive noise and received by the receiver. So here, Shannon argued that it's this noise that limits the rate of transmission, and that's what the channel coding theorem says. And this noise actually is a kind of equivocation. For example, you have different transmitting messages, but they all correspond to the same message. That's equivocation. So how many messages you can transmit at most depends on the degrees of equivocation, right? For example, within the same frame, you only should pick one signal or one message to transmit, because you don't want to have your results equivocate to each other, right? And that limits the number of messages you can transmit. right? So using these notions of equivocation and the visual representations of Venn diagram, Shannon came up with his famous channel coding theorem, which represent the channel capacity as the maximum number of unequivocal messages. And along the same lines of thoughts, Shannon came up with further representations of the channel noise in terms of the signal and noise ratio. So for the continuous white Gaussian noise and continuous signals, he came up with this famous formulation of channel capacity. So this was obtained from a very highly geometrical and visualizable scheme. So he did this by first sample the continuous signals in terms of a number of sampling points, right? And then he represent each continuous waveform in terms of a points based on as the coordinates of this high dimensional signal space, right? So for a channel with corrupted with noise, each signal has a sort of noise sphere surrounding the signal points. So in order to achieve the channel capacity, you have to make sure that these noise spheres don't interfere with one another. Therefore, the channel capacity problem ended up with the sphere packing problems, in which you need to pack sufficient number of spheres in that big signal space, but don't let those spheres overlap with one another, right? So these thoughts about the signal and noise in communication theory actually later on offer some further inspiration for the communication engineers after World War II. And that was the idea of the so-called spread spectrum. So the idea is, following Shannon's information theory, we can use this noise-like characters of signal or make the signal more noise-like in order to achieve higher channel capacity or higher signal to noise ratio, right? So in more specifically, we can code signal with random fluctuations or randomized waveforms or something like white noise. So after World War II, quite a number of engineering researchers endeavor to find ways to code signals with random noise-like waveforms. So for example, the New York-based engineers Mortimer Rogo's Noise wheel or Lincoln Labs' NOMAX system. They're both examples of this so-called spread spectrum communication. So in the first part of the 20th century, we've seen that these different thoughts and materializations of noise came to the fore, and they began to point to more abstract and more generalized notions of noise. So after World War II, of course, all this took off further, and this talk about noise as the random fluctuations at large, as signals, as information became more and more popular. So just take a simple example or simple experiment from the Google Ngram. So by typing signal, noise and signal together, we can see that the number of publications had a surge around the 1940s. And that happens in technology and engineering, in physical sciences, life sciences, and social sciences, in a lot of realms, right? And once again, so these developments after World War II testify to ontological development, epistemological development, and technological development, right? So there's some new notions about the actual fundamental existence in nature that have this random properties. That's ontology. And there's this thought that our knowledge about the world actually is limited and it's intrinsically random. We can only handle this by using the statistical methods. That's epistemology, and we can also see a lot of new techniques, both material technologies, but also mathematical techniques developed after World War II, along with these lines of random fluctuations. So I guess in the end, I want to emphasize again that the centrality of sound, chance, and information in these transformations of noise. I would also like to say one thing or two about like how to understand this overall historical process, right? So traditionally, or a sort of a more common way among historians of science and technology is to understand this conceptual development as a kind of historical epistemology or historical ontology, which point out that changing understandings, changing standards of objectivity or changing understandings of the existence of the world through history. But here I want to highlight that this is not just conceptual. This is not just about thoughts and theories. In this developments, we can also see a lot of material objects, see a lot of considerations about the sensory experiences, about sounds, and also about material practices. So with that, I conclude my talk. Thank you very much. Yes.
So if I think about, sort of the history of physics, one type of noise that kind of pops up more immediately in the 1960s was the cosmic microwave background.
Yep.
And what's interesting about that is that it was treated as noise initially by Penzias and Wilson, and then obviously people not too far from here realized that it was something much more significant. And so it transformed from being a noise to a signal, or at least a signature. I just wonder how that fits into your thinking here. Is that an ontological thing or something like that, and whether or not it has any other ramifications?
Yeah. So indeed, yeah. So this cosmic noise started as as sort of background noise in radio astronomy, but then became something very interesting. So in my book, I tend to treat this as sort of epistemological issues leading to some kind of ontological issue, right? So Ian Hacking, the famous philosopher of science, had some discussions along that direction, right? So Ian Hacking talked about debugging in the sense that when you have measurements, scientific experiments and measurements, and the result doesn't go like what you expect, then you're trying to figure out what's the case, where does things go wrong, right? And then that's a process of debugging. And in that process of debugging, you sometimes find trivial mechanical problems or device instrument problem, but sometimes you find that the problem is not that trivial, right? The problem has more to do with our previous bias or our previous ignorance about some new stuff, new entities, right? So this debugging process has some kind of open-endedness. So this is an epistemological or epistemic process. But at the end of the process, we can see some, we have the chance to identify some new entities. In the case of cosmic microwave background, exactly, that's a new physical phenomenon. So that leads to new ontology. So I would characterize that that story as a sort of trajectory from ontology to epistemology.
Brad?
I was going to ask about the politics of noise. Also, I think in terms of the sonic noise, you've had a growth over the last decades of kind of anti-noise movements that modernity is somehow fundamentally too noisy and we need to return to silence.
Yeah.
And I'm wondering, when you look at this story of this transformation from sound to signal and information, if there's also a sort of related political transformation, or if noise becomes somewhat less political in its transformations.
Yeah, so I so in that sense, well, basically politics loom large in a lot of these developments, right? So when we talk about, let me just pull up that page. Yeah. So when we talk about the notions of noise as intrusive sounds, as nuisance, there was a significant political backgrounds in terms of what constitutes the intrusion, right? What constitutes the right sound, what constitutes the incorrect or the wrong kind of sounds, right? So that's a cultural problem. That's also a political problem that can lead to can have significant consequences, like where you should locate your factories or your shops in the neighborhood, etc. But in the broader realms, you can also talk about this corporate research on telecommunications, mass media, sonic soundscapes of sound reproduction entertainment, right? So it's capital on the one hand, it's also it's also politics on the other hand. So there are multiple like political backgrounds in this developments about the understandings and measurements and the coping of noise. So I guess my focus here, okay, so my approach here is that when the narratives, when the sort of traces of developments encounter political circumstances, I discuss them, I deal with them, right? So like the World War II situation, the World War II story, all these researchers had some very politically motivated reasons to engage in the noise research. So I pointed that out, I engaged that. Similarly, for the sound reproduction technology, their background, like Addison's research on this surface noise, there was a commercial, vis-a-vis, there's a commercial reasons for that, so I engaged that. But the what I want to trace here is the sort of conceptual technical developments of noise in different circumstances. But definitely, I welcome that historians and scholars who are more interested in the political and social and cultural aspects of this process utilize my findings in this way or that way, cannibalize my findings. So definitely that's not a problem for me. Yeah.
I had a question which goes back to the audiometer and the human balance technique.
Okay.
What strikes me is precisely because the role of the human and the role of the ability of these people to hear.
Yes.
Right. I mean, it's going to be a function of how good, I'd be interested to hear who these people are that they choose. The second question is, as it becomes more, quote, objective, unquote, when it turns to the visual. So audiometers succumb to oscillographs, oscilloscopes, or frequency analyzers. And particularly for sound technology, you can have by the 1920s, late 20s, as you well know, I mean, Bell Labs can tell you the overtones of a Steinway piano very, very well.
Yes.
My question is, there are interesting debates in Germany that say, where the question is, the expert hears something that the device doesn't show. And that's because of the properties of human hearing, right? So it's nonlinear, so that we can hear frequencies like, I'm making this up. No, I'm not making it, about 1,000 to 3,000 hertz really well, 100 not so well, 10,000 not so well at all. But they're also, because of the physiology of the ear, you hear combination tones, right? Where you have two tones and you're convinced you hear a third tone.
Yeah.
Sometimes that's a product of a musical instrument. Sometimes that's the product, they're ghost tones or subject tones. They're products of the human ear, which an oscillogram will not give you.
Yeah.
My question is, are there debates about at AT&T about, well, this expert listener or hearer whom we found because, I don't know, he's a concert cellist. Cellists are the best musical instrument, by the way, musicians in the world. They're actually, and this is no joke, cellists are actually used for sound detectors, and I'm always for submarines. And if anyone finds out why, I'll give you a bottle of cheap bourbon. So the question is, what happens when you have mechanical objectivity, footnote, which is just as subjective as Jonathan Stern will tell you as the subjective. What in the politics of that? What happens when an expert human says, "Well, actually, you expert engineers are wrong," because that's not what I hear at all.
Okay, great. That's a great question. So, in brief, the kind of sounds that these engineers, these people were dealing with were sort of different from the kind of sounds that you were dealing with, right? So it's not about, at least for the AT&T ear balancing method for measuring atmospheric noise or electronic noise. This is not like high fidelity music, not like Wagner's opera or Beethoven's symphony. So these listeners were not super picky about the quality, the tonality, the tone colors of sounds, and therefore the intricacies of hearings, sort of physiological effects, didn't play a part for most of the time, right? So, because for most of the time, what they wanted to know is that how loud is this sounds, right? So that's it. However, that says, as I said, well, I pointed out the sort of debugging and epistemology at the end of the process, but that kind of thing also happened early on. So more specifically, when experimenters were doing some experiment using apparatuses like audiometers, and they got some results, but the results just didn't work out. And then they go back to see, well, whether there's anything wrong with the audio, with the sort of human perception. So that happened exactly when in the early 1920s, another researcher at Siemens Hauske Gesellschaft, Carl Hartmann, and he was trying to measure, to produce experimental verifications of Schottky's theory of shot noise. And then in his first round of experiment, he got something which was very wrong, right? Which was very different from Schottky's theoretical prediction. And then he was trying to figure out what happened. And then he went through this debugging process and then tried to argue that, okay, so we use this ear balancing audiometer, but in using this, we actually ignore that the human perception works in a logarithmic way, the Weber-Fechner law, and there are all kinds of corrections that you should make. And after you make this correction, the data look better, etc. So that doesn't happen in the realms of trying to capture the scientific objectivities of music, but it does happen when they're trying to use this method to get something more than gauging the environmental sounds, but to get some experimental results. Yeah.
Sonia.
Thank you very much. I have basically 3 questions. The first is noise studies were made in different countries in the same period. Were there different focal points, different approaches than those that you have described? That's the first one. The second one, in September in Athens, I listened to a couple of Greek colleagues talking about the usage of noise in combating political enemies, to be concrete, camps in Greece against the communist rebellion. And the manual they used was a CIA manual about how to use noise. Is that part of your research? Are you aware of that? And how does it relate? And the last one is, there is this long-term project on sound by Victoria Kacek.
Yeah.
How does that overlap with yours?
Okay, great. Yeah, so for the first questions about the noise studies in different countries. My materials, my treatments are definitely selective. So in this book, I try to transgress the national boundaries whenever I can. So that's the reason why, in the early chapters, I have a lot of discussions on the European theoretical developments on random fluctuations. So You have Einstein, Smoluchowski, Langevin, you have Schottky, etc. So these were European physicists. So they have their different sort of little research traditions on random fluctuations. And then for the material studies and material engagements of noise, I admit that I focus more on the situation in the United States than in Europe, right? So I probably shouldn't say too much about like what happened in other countries in terms of this material engagements of noise. So, for example, Miles knows much more about what happened in the German states with respect to the noise, right? So, yeah. So, but my hunch is that for the theoretical studies of random fluctuations, so this is what happens here is more or less the sort of a more common disciplinary matrix, which some American mathematicians and physicists were working on that, and some European, some like Germans and French and Russians. So they're all working on the same, similar problem sets and problem situations. So for the noise technology, for the noise engineering, so similar technologies could have very different political and societal and sort of economic implications, right? So this book forthcoming by Miles, so for example, it talks about this German electrical musical instruments. So there are a lot of technical overlapping between what happened in Germany and in the United States, but the cultural connotations and the political ramifications were entirely different, right? So I think you're absolutely right in the sense that if we look at the political and economic, cultural, social aspect, then there can be a lot of differences. But I just don't have enough knowledge about this. And whether there are like genuine technical differences between these research communities in different states, I probably won't be able to say too much, given my limited understandings of the other countries. And for the use of noise as a sort of weaponizations of noise. So I'm aware of that I don't do study on that topic, but I am aware of that. I think there's a huge area to be explored about the sort of physiological and human sides of noise, right? So how noise is perceived, sort of what's the effects, psychological, physiological effects of noise come forth, and how that figures into technologies and the culture and society. So I know there's a huge story to be told along that direction. So in this book, I pretty much focus on what happens outside the human ears, right? So I do engage in this occasion, I do engage in the perceptual issues, right? The voice and hearing, etc. But by and large, my focus is more about the sound technology, sound reproduction technology, the random fluctuations, the information technology, so this kind of things, which are highly mathematical and theoretical. And that leads to my answer to the third question, which is this research program's relationship to Professor Victoria Katz's research. I think her research also focuses more on the physiological and the psychological effects of sounds, right? So, and that's wonderful because she tailors together these different narratives about, for example, the internal voice, the internal sounds, that you can address this from the perspective of continental European philosophy or psychoanalysis or physics or physiology, acoustics, etc. So there are many dimensions, there are many aspects to be said about this this kind of research. And in the future, I hope I will be able to address more the issues of sounds and hearings and perceptions. So yeah, maybe in my book about the Chinese linguist Zhao Yuanzhen, I'll be able to say more along that direction. So in this book, the sort of engagement with perceptions and audibility, the hearing, articulation. So this kind of engagement is quite limited. Yeah.
One last question. Yep. Mark.
Thank you so much. Sonia's question actually made me sort of click the thing I wanted to ask you to try and figure out. There's a normativity to sound throughout the talk, that it's something you're wanting to control, eliminate at the technical level, at the epistemological level. There's even some sort of ontological point about the normative relationship of sound, of noise rather. And so I wonder if there are moments in the story where that breaks, where they're trying to produce noise, or I'm thinking a lot about how in the case of differential privacy, we really want to produce a lot of noise. The production of noise is the goal. And so maybe, Shannon, are there moments where that normativity sort of breaks down?
Yeah, that's a moment. Yeah, so at the end of this story, I deliberately highlight spectrum technology communication, which is exactly the situation in which these engineers and mathematicians like Shannon figure out that the best way to combat noise is to use noise, right? So therefore, they deliberately try to make their signals more noise-like by modulating it with some random fluctuations, right? So that appears in a lot of technologies today. When we talk about computing, communication, information processing, like our cell phone, we have CDMA built in, which is exactly a sort of subsequence of the spectrum communications after World War II. So, so indeed, if I have a chance to write like volume 2 of the book, then definitely there are a lot of situations in which these scientists or technologists or engineers, they appreciate or they understand the importance of noise in the either like stability of the systems or higher like engineering efficacies or like healthier ecosystem, etc. So yeah, so moving to the second part of the 20th century, that kind of situation become much more frequent. But at least here, I highlight one in the realms of engineering. Yeah.
Right. So I just want to say many, many thanks for a wonderful discussion and
very
paper,
much.
Chen-Pang. Thank you.
Thank you very much.